He will not force
Well, Roger, it's very nice to talk to you in this strange interview format. Someone I've talked to for 42 years.
A long time, yeah.
So we're rehearsing all sorts of things that have come up during that period. And I suppose my thought goes immediately to time. I mean, everything you've done seems to be like defeating time in one way or another.
Being defeated by it normally.
Well, I don't think so. I think you've defeated it more than most people could ever have done.
I don't know whether you remember my office where I used to have a clock that went backwards.
Well, that would be a good motif if we wanted one in the background, I think. But certainly we're thinking about second law of thermodynamics and the mystery of time direction and our consciousness and our awareness of the past. And so we can only talk about the past, unfortunately. It's a great disadvantage that we have. But I was thinking perhaps you would like to say something about how your first mathematical work, perhaps in the Cambridge, I'm sure it started earlier, but at Cambridge in the 1950s, it seemed to me that so much came out of that, and there are still some puzzles for you then which are still very much around now.
Well, I started off by doing algebraic geometry in Cambridge as a graduate student at St John's College. And I think I was misled into thinking that algebraic geometry was geometrical. And I very soon learnt that it was basically algebra, where geometry was the thing that I enjoyed and found I could do most easily. So one thing I did was to develop a notation which, well, Hodge was my supervisor originally, and Michael Atiyah was one of the people, a contemporary of mine at the time, which was rather terrifying because I thought all graduate students were like that. And it took me a while to learn that there was something particular about Michael. But I developed a notation initially sort of to handle Hodge's lectures, because he gave lectures on differential geometry, and he had these indices all over the blackboard, and it was not the easiest. His were not the easiest lectures to follow, and partly stimulated by that, I developed this notation where tensors could be represented with blobs with arms and legs, and you could stick them together to form contractions and so on. So it converted algebraic problems to do with tensors into pictures, which I could understand much more easily.
Well, that's a whole motif which I was going to ask you about later, in fact, the number of ways in which you develop ways of seeing things on the page and in one's mind that's quite different from the usual way of formal notation. But also it just strikes me that, I mean, you didn't follow the kind of algebraic geometry of the more abstract kind that's been so enormous since that period. There were tremendous things going on with the abstraction of mathematics, but you kept to a geometric viewpoint, which must have been very unfashionable, really, in the Cambridge of that period.
I think I was very unfashionable. Although, if you look at my thesis, there's not a single diagram in it. But it was all done using... I mean, there were diagrams because I did the algebra by making these tensor pictures and drawing lines and having notations for symmetrizations and skew symmetrizations and things, and how you manipulated these things. And although it was very algebraic what I was doing, it was done in a very geometrical way. But I think one of the big things that was important in how things developed with me was I developed this general formalism of tensors which went beyond the normal idea, and you could include things like negative dimensional tensors. And these turned out to have relevance to spin in quantum mechanics. But one of the things was I was very mystified by spinors, because they seemed to be fractional things where you had a square root of a vector or something like that, and I couldn't understand how you could do that. And Dennis Sciama, who was a great friend of mine when I was in Cambridge, quite early on he sort of we made good friends, and he was a cosmologist who was very much following the Cambridge line at that time, which was the steady state model of cosmology. Because Bondi and Gould and Hoyle were all there, these being the originators of this idea, and Dennis was a strong follower of it, which I found very interesting and intriguing, and philosophically a satisfying picture, where the universe sort of was there all the time. It didn't have a beginning, and the expansion of the universe was compensated by new material which was created continually, which I had problems with later, because it was hard to see how you could combine it with the rules of general relativity. And given the choice between general relativity and the steady state model, I would go with general relativity. But my friendship with Dennis was very important to me, because I learned a lot of physics from him. You see, I was doing pure mathematics as a graduate student, but there were at least 3 courses of lectures I went to. There were a lot of pure courses I went to which were important to me. I remember Philip Hall's courses. Sean Wiley gave a very nice course on topology and things like that. And but then I also went to other things which were not really evidently anything to do with what my research project was. One of these being a very beautifully done course by Bondi, Herman Bondi, on cosmology, general relativity and cosmology, which was done with great flair and a wonderful course. And another course, equally brilliant in a completely different way, was Dirac's course on quantum mechanics, which was, everything is very logical and very beautifully organized. Many of my colleagues said, oh, well, that's just the same as this book, you see. So I said, well, I hadn't read his book, so the elegance of what he'd done came out in his lectures. But it was also important to me because, for some reason, I don't know whether Dennis had been talking to him or something, I wasn't quite sure, but it was a course on standard quantum mechanics, which was the first term. And then the next term was to be on quantum field theory. And in this course, he took 1 week off to talk about two-component spinors. And I had been trying to understand from reading various incomprehensible books about two-component spinors, and they made no sense to me at all. But these, I think it was probably 2 lectures Dirac gave, and they were just perfect. It became completely clear, the whole subject, which is a bit ironic, because people think of Dirac as a 4-component spinor man. But he, in fact, not only understood about two-component spinors, but he developed the higher spin versions of his own equation using this formalism. And it seemed to me it was absolutely the right way to do it.
So you've already mentioned, I mean, I'm thinking that when I was at Cambridge, it was very much divided, pure and applied, and people hardly talked to each other at all. I mean, in my time, they were in separate departments, and you had, as an undergraduate, you were supposed to choose which you were, and you just stuck to it. There was a real cultural block there, but you just ignored that. That's
I think I ignored it, yes. Well, Dennis was all the time trying to get me interested in physics. I had a conversation earlier, before I went to Cambridge, about the steady state. Wonderful lectures given by Fred Hoyle, which there were some issues which I couldn't quite make sense of, and I got talking to Dennis, who was a friend of my brother's. My brother Oliver, who was at Cambridge several years before me. And so we struck up a friendship with Dennis at that point. So he was trying to get me to do physics all the time and get me interested in physics and maybe convert my subject to physics, which I never did, because there was there was too much in the mathematics that I was very much involved with and interested in. Tensor systems in general, geometry ideas, and so on. And a lot of these ideas which I should have learnt then, you see, one of them in particular was about sheaf cohomology, because, well, they used to call them stacks in those days, theory of stacks, you see. I think stacks still mean something, but at that time it's what became were called sheaves, I suppose. And I was baffled by the whole thing. And it was only many, many years later when Michael Atiyah made all these things clear. But at the time, I realized there were things that would have been very useful to me later on had I paid adequate attention then.
What did William Hodge think of your studying all these different things? Was he aware? I mean, I just think to many graduate students now, they'd be horrified by the idea of studying all the completely different courses and not getting going on publishing the papers of the right number and the right
Maybe
places.
Maybe a bit different then, but there was also a slightly strange thing about, you see, I started off with Hodge, and well, there were two other students. One of them gave up quite early. Another one was Michael Hoskin, who went through and did his PhD, but then went into history of science. And the other one was Michael Atiyah. And as I say, I thought, that they were all like that, more or less. And it was quite, because Hodge suggested at one point, well, if he sensed I was a little unhappy with the very algebraic problem that he'd set me. And so he said, well, you might like to sit in one of the classes of another student. So that was, I didn't understand a single word of what was going on, but that was Michael Atiyah, you see. And I later became very good friends with him. There was another course that I went to when I was at Cambridge at the same sort of time as when I went to Dirac's and Bondi's course. This was a course by a logician called Steen. And I went to that, which I also found was very influential on what happened to me later on, because I learned about Gödel's theorem. I'd vaguely heard about it before, and I found it rather disturbing. You see, I think I would have, prior to going to Cambridge, believed, we're all computers, and that's what thinking is computation or something, mainly because I couldn't think of anything else. And Gödel's theorem I'd vaguely heard of, and it was sort of touted as something which was showed there were things in mathematics that you couldn't prove. And then when I went to the Steen's course, it made quite clear that although you couldn't prove them using some particular system, the mere fact that you trusted that system is something you could derive reliable conclusions from, that mere belief in the system enabled you to transcend the system, and you could find statements which had to be true on the basis of your trust in the system, even though you couldn't prove it using the system. So I found that very striking.
Did you even at that time have some inkling that there should be some connection with the physical description of the brain and of matter generally?
I think I did, but it wasn't very well formulated. You see, I think I probably did, as a result of Steen's course, come to the view, because I learned about Turing machines as well, that was all part of the course, so Turing machines and Gödel's theorem. And the fact, therefore, because of this understanding that seems to transcend any particular formal system, that there must be something else going on in the brain which is not of a computational character. And I probably learnt from Dirac's course on quantum mechanics. There again is a bit of an irony, because I remember the first lecture I went to, he had this little piece of chalk. I think he broke the piece of chalk in two or something. He was talking about superpositions. In quantum mechanics, if you could do one thing or another, then you could have superpositions of the two. And so he said you could have a superposition of a piece of chalk over here and over here. And my mind wandered at that point, you see. And I remember him saying something about energy or something, but I couldn't understand why this was an explanation of anything. I thought it must be because my mind had wandered at that point that I'd missed the point. But it worried me ever since. And I think I did formulate the idea that there was a big gap in our understanding of the world, in quantum mechanics specifically, and that there probably was some link between that and what must be going on in our conscious thinking. But it was pretty vague, and it was only very much later when I heard a radio talk when Marvin Minsky and Edward Fredkin were talking from a very computationalist point of view. And I could see, well, from that perspective, then I see why they're taking that view, but it seemed to me ridiculous to extrapolate to that degree. And this was what made me realize that I had something to say on this subject, which seemed to be different from what other people had been saying. So I had the idea that in the very remote future, I would write some book about trying to get people excited about mathematics and physics, but it didn't really have a focus. But then this thing said, oh well, I shall try and describe my ideas about what's going on in the mind.
I suppose we should, just in case people may not be so familiar with the time scale, what we're talking about, because this really only, what you're talking about now was the work which came out in The Emperor's New Mind.
Yes, I'm leapt ahead, yes.
And in fact, you started publishing on this in the mid-80s, and the book was what?
That was probably in the 80s, wasn't it?
Yes.
Yes,
And perhaps we should just remind people that the cosmological picture, as you were studying it from Dennis Sciama, I mean, it was hardly anything was known at all then, really. It was just the really comparatively local expansion of the neighbouring galaxies.
Well, I think
terms,
people
I guess,
regarded cosmology as just philosophy or something.
Yes.
I mean, there was no reason to believe one thing or another. And it became, well, it was the microwave background.
But that was only later.
That was
discovered.
much later.
So when you were introduced to it, it was it was not exactly a clean slate, because the Hubble expansion was known, but nothing like the detail of today.
I'm afraid I am jumping around here. You're quite right.
But that's just interesting, because you took up subjects which then would have been comparatively low profile. I mean, relativity as a subject was not. I mean, Hermann Bondi put the new modern ideas into it.
I think Bondi was a big influence. Yes, he gave some radio talks which were extremely good, very clear. And he certainly influenced me a lot.
Yeah.
And put the subject, well, it was a very physical way of talking about things, but it was extremely clear. I think I learned a lot also from other colleagues. Felix Pirani in particular was somebody who I learned a lot of the mathematics of relativity from.
So I think that's where where you were able to put two of these otherwise completely disparate pieces of knowledge together, which is understanding of the null geometry and the spinor representation being relevant to general relativity. How did that's something which came out of geometry and relativity that. Yes,
I have to try and think of the order in which these things. I got interested in the physics, and you see, Dennis was he knew everything that was going on in the world of physics, particularly cosmology and astrophysics and that kind of thing. But he also was interested in the foundations. And he used to drive, sometimes we'd go to Stratford and go to plays, you see. And he would drive in his fancy car, you see, at great speed. And as you went round the corners at this great speed, he would say, now that's the action of the fixed stars, you see. Because he had this Mach's principle idea was very strong with him, that somehow what determined the local inertia was the distant stars and the galaxies, with a sort of Machian idea. And if you were Newton's rotating bucket, you see, it's the reason it bulges at the edges, because the influence of the stars is sort of pulling it round, you see. And we used to have these discussions as we would drive to or from Stratford. And the idea would be, well, suppose the stars or the galaxies, we got rid of them one by one, what would happen to inertia, you see. And so I tended to take this to an extreme. So, well, there's nothing left but the car, you see. Well, then would you feel anything, you know, that the inertia would be, according to this view, fixed by the car itself. So I'd go down and say, well, suppose you just had two electrons, you see. Then how do they know how they're spinning? Or one electron, you see. Well, one electron, does it know which way it's spinning? Or if you have two, or if you have several? And so I started thinking about individual spin systems where you had no notion of direction. It was only what the total spin was when they came together, and you bring another one in. Does the spin go up or down? What are the rules, you see? And so I developed this idea of spin networks basically from that idea.
I hadn't realised that the spin networks were as early as that, and therefore related to your to the negative dimensional tensor and the diagram calculus that you'd worked out.
That's right. That all came in. That all came in very early. Yes, and then you see the connection also between the dimensionality. See, this was a thing that intrigued me very much. Was how you have with spin, you take an electron or spin half particle, then it's only got two ways it can spin, you see. But how can you have two ways when it's got the whole sphere of directions? Well, that's because of quantum mechanics and spin up and spin down, and all the other spins are combinations of them. And then you see the array of the complex combinations of two states, which is really a sphere, and that sphere gives you the directions in space. Well, there you have an intimate relationship between the three-dimensionality of space and the complex numbers of quantum mechanics. And so this kind of struck me as something deep in a way. And then also when I started thinking more about I can't quite think of the order of this, but the relativity picture, where you now have the light cone and you have the directions along the light cone, or if you like the sky, celestial sphere, and you have the different directions on the different points on the sphere. And then again, it becomes useful to represent those as points on the Riemann sphere, the complex plane together with infinity. And that sphere is physically a very natural way of thinking about the directions in space.
Yeah, you see it all the time.
Yes, absolutely. Yeah. You go out on dark night and you see...
Well, we see the past anyway.
You see a little bit of it. Yeah. But out in space, of course, you have a better picture. But somehow, thinking of that as the complex sphere was a very crucial way of and nailing down the space-time dimensionality, 3 space and 1 time, and only then do you get a light cone, which is a complex structure.
So you had Dirac's 2 spinners, which is completely contrary to most. I mean, people would think that he was wedded to the four spinner and the gammas and everything, and yet that gave you an insight from quantum mechanics into space-time and relativity, which is, again, not the direction one would naturally think of.
No, I just went off. I tended to go my own way. I think, I mean, I was always, you see, when I was at school, I remember particularly in Canada, I was in Canada during the war years, and I was extremely slow. And you need my mathematics papers. I wouldn't get very good marks. And in fact, once I got moved down a class because I was very bad at doing mental arithmetic. But there was a teacher, we had a very insightful teacher, Mr. Stinnett, I think he was called, and he realized that if I was given enough time, I might do rather well in the tests, you see. So he said, all right, we're going to have a test today. It's the whole, usually just this period, and you're supposed to finish this, but I'm going to let you have as long as you like. So I would be working away. The next period would be a play period, and people would be outside enjoying themselves. I'd be still plugging away. Occasionally, I'd go on into the one after that, still working away at this test. And then I would do very well. I would get, 98% or something. And it was a huge difference. And I think the thing was that I was not good at remembering things, you see, if I had tables or whatever it happened to be. But if I had enough information so I could work it out each time, you see. So I think it was something I always tried to work these things out for myself. Of course, that's not much good if you're trying to do a school exam. But later on, it kind of served its purpose. So I had to think these things on my own terms, rather than learning about them from a book or whatever it was.
So I would guess that if you put forward these... the particle physicists of that period wouldn't have been very interested in whether it was 2 spinners or the relationship of SL2C to the and this kind of thing. But your direction went into relativity, but really you had a great deal that was coming from quantum mechanics as well as from classical geometry in the background. True. Is that
Quantum mechanics certainly was a big influence on me. Yeah. I mean, I don't know exactly when I firmly thought, well, something's got to be done about quantum mechanics, that you have to change the rules at some level. I think I felt that pretty early, but I couldn't put a date to that. But nevertheless, the idea that quantum features very fundamentally at the level of small things, yes, that was crucial.
And what point also is just understanding the importance of null coordinates and the light rate and the conformal structure and the metric as secondary, and your observation on the moving sphere in 1959 is just such just a 2-page working out of that idea, but it destroys a whole lot of talk about people being squashed up when they move in relativity. Was that? And that was. I'm
that
not
was
sure
all
where
part
that
of it.
comes in your publications, but fairly, it's...
It was before you see, I went to America. This was probably I went to America in '59, I guess it was. In 1958, I went to a conference on general relativity and gravitation in Royaumont, near Paris. And that was shortly after I'd been thinking about spinors and relativity. With Dennis Sciama again, you see, he was very keen on getting people together who he thought might have something to say to each other.
And I think, am I right, in '55 was the first General Relativity conference, and '58 must have been the second. Is that? I mean, it's very early days.
Yes, it wasn't the first. The first
right?
one was probably Chapel Hill. I can't remember. There were two, and I can't remember which was called the first one.
I see.
Chapel Hill was one, and Paris was the second.
But it would have been a comparatively small body of people.
Relatively
who took
speaking,
any interest
but
in
there were a
this.
lot of people I got to know well and knew them later on. Ted Newman, lots of people. It was a big influence on me, but it was important to me because, well, let me just backtrack a little bit. It would have been '57 probably, I'm not quite sure the date. But Dennis persuaded me to go down to King's College London, where David Finkelstein was giving a talk about the Schwarzschild solution and getting rid of the singularity or something. So, that sounds interesting. I wasn't working on general relativity really then. You see, I was thinking about these spinors and so on. And he gave a talk where he showed how you could extend the Schwarzschild solution to within the horizon, what we now call the horizon, but people used to think of the Schwarzschild singularity. And he did it in one past and the future, and then showed how to stick these together into what was now called the cross-call extension. And this made a big impression on me. But it was kind of curious because Finkelstein at that time his main interest was general relativity, and mine was in spinors and playing around with things in the small and quantum mechanics and so on. And we, in a certain sense, or combinatorial, I was doing spin networks. And so I explained to him about spin networks. And he, from then on, went on and did combinatorial things, and I picked up and did general relativity after that. So we sort of swapped roles.
But I can see how that would have touched all sorts of things. It needs the null coordinates to do that.
Well, it was, you see, there was, the history of it was sort of like this. I went to the lecture, and I was very impressed by how you got rid of this so-called Schwarzschild singularity, but you still had the singularity in the middle.
Yes.
So I thought somehow, okay, you've pushed it from one place, but it's still there. So I began to think, is there a general argument to show that singularities have to be there? Now, I had no mechanism, nothing to try and tackle this problem. The only thing I had, which I'd been studying, were the spinors. So I thought, well, look, let me just see how spinors work to try and describe relativity. So then I did that, and I looked at the Weyl thing, and it all kind of came out so beautifully. And the Weyl curvature being totally symmetric spinor and all this stuff was
and no one else had done that. But Felix Pirani did things. Was that?
It was Lou Whitten, Ed Whitten's father, who had. I didn't know about it. Felix Pirani mentioned there was this paper by Lou Whitten, where he had actually applied spinors and looked at the invariance. There were some things which weren't quite right in the paper. I sort of looked at it and corrected that, and did some other things that he hadn't done, like the canonical representation into 4 principal null directions and so on, and all that stuff. But somehow it all fitted together in a much more beautiful way than I had thought. And it was as much that as David Finkelstein's lecture, I think, which dragged me into studying general relativity in a serious way. I'd been interested in it before that. My first interest, curiously enough, my first encounter with general relativity, apart from my brother Oliver vaguely describing it to me, was a little book by Schrödinger, Space-Time Structure, which is a really nice little book, apart from the last chapter where he goes on to his own funny ideas. But most of it was a very beautiful explanation of the tensor calculus and so on. So I learned about that even before I went to Cambridge. But then picking up things from Felix Pirani and Dennis, and so and then I went to the Royaumont conference, which was in '58.
Yes, that's
58, I think. And Dennis very generously, he was one of the principal speakers at this meeting. He said, well, look, I've got an hour's talk given to me. I'll let you have half my time. I thought that was extremely generous of him. So I gave my little talk on the spinners. I forget whether it was an hour and a half the time, whether it was 40 minutes and I had 20 minutes, I can't remember. So it was a rather hurried little talk on showing how you translate these tensor quantities into spinners and how beautifully it fit in with the ideas of general relativity.
That was actually motivated by what became the singularity theorems in the mid-60s. But that was before you'd actually, I mean, this was before we really started on publishing.
Yes, there were certain. Yeah, well, I published the thing on the spinners.
Yes.
Which is 1960, but then it was more. I went to Princeton. I was in 2 years, well, a year and a half in Princeton and Syracuse, and I got influenced by John Wheeler, I think, on the idea that you have, or it may have been a little after that. Yes, I think it was that there was a conference in Warsaw where that's where I started talking about conformal infinity, and I think then in the mid-60s, early 60s, it became clear from the observations by Martin Schmidt that these were the first observations of quasars. And I remember Wheeler getting very excited about this and saying, look, this tells us there are objects which are really down to the scale of their Schwarzschild singularity. Before, we always used to think, oh, well, this Schwarzschild so-called singularity was a tiny little thing, wouldn't have any relevance to physics whatsoever. But here, it became clear that there was something funny was going on, where you really had things which varied. They must be sufficiently big because they're this energetic, and they must be sufficiently small because they varied within weeks or days or weeks or something, so they can't be too big, and therefore they must be of their sort of size that their Schwarzschild radius was. That was what we now call a black hole, and the name black hole hadn't emerged at that stage. But Wheeler was very interested in this idea about whether singularities were generic or not.
Were you aware of you were aware of Oppenheimer's 1939?
Yes, well, this was something that Wheeler made a big point.
Yes, he would have known all about that.
Yes. So the various papers that Oppenheimer was involved in, and particularly the Oppenheimer-Snyder paper, where just before the war, where you had this collapse of a very artificial material, sort of dust, and very artificial, and it was exactly symmetrical. And then he had this model of it collapsing to a point. But it was regarded by many people as highly artificial. These idealizations wouldn't apply generally, particularly because the Russians, these were Lifshitz and Kalatnikov, seemed to have proved that the singularities were a very special thing and they would not occur generally. Now, I'd sort of seen a little bit about their proof, and I couldn't imagine you could really prove something like this the way they were doing it. So I started trying to think about this in other ways, geometrically, kind of visualizing what it would be like inside a collapsing star, and trying to, convincing myself it had to be a non-local argument, that you wouldn't be able to prove anything from purely local considerations. And then there was this idea about what's called a trapped surface, which came about in a rather curious way.
Oh, so
well, I was talking to Ivor Robinson. I was at that time I was in Birkbeck College in London, and Ivor Robinson, who was a friend of mine, I learned a lot of things about spinners and self-dual things and so on, which became important later in twistor theory. And he was talking about something completely different, politics probably. And we came to a street, and across the street, and conversation stopped then. And then we got to the other side. He started talking again, you see. And then when he went home, you see, went where he was going. And I remember thinking at the end of this, a feeling of elation. And I couldn't pinpoint it. Now, why am I feeling like this? You see, so I went back to all the things I'd been thinking of during the day. And then I remembered crossing the street. And when I was halfway across the street, a thought occurred to me. And this was evidently this characterization of a collapse, what we call a trapped surface. That this characterization, which was a global condition, and it tells you that this star has reached a point of no return. And so when I realized that idea, I then developed pretty well the same day, roughed out a proof that you had to get singularities. But that's misleading in the sense that the techniques were things that I had developed a bit earlier, partly, although never published, as an argument going back to the steady state model, because I was interested in steady state, but I also interested in general relativity, and I was trying to see, is it possible that you could have something like steady state consistent with general relativity? If it was an exactly symmetrical case, you could see there'd be problems with energy. But if it's irregular, maybe you get away with it. But then I developed an argument with these cones and focusing and so on to realize that that wouldn't help, that you'd still be in trouble. I never published that. But there was an argument in which was another thing in the Royal Society. I had to try and prove something about asymptotics, which I wasted a lot of time. But I developed these techniques. I thought I was wasting a lot of time, but I developed the techniques which became just what were needed in the case of the collapsing black hole.
So those ideas in differential geometry and topology, which you needed there, were developed for the problem of the 50s with steady state, which was where she was blasted. I mean, as soon as the Big Bang was the
microwave background,
it was discovered that it was really out of the picture.
Yes,
but it turned out just the thing for black holes, which were fantasy in the 50s.
Yeah.
But very far from fantasy now. I mean,
that's right. Well, it was curious how the thing developed, because the first I went to a lot of the early, what are called the Texas conferences on relativistic astrophysics, and I went to the first one, which was a lot of the stuff about the quasars, these things that Martin Schmidt had seen and Wheeler was very excited about, and so on, and Roy Kerr at that point had found the solution known as the Kerr solution, which can be interpreted as a rotating black hole. It wasn't totally clear at that stage that you could interpret it that way, but this did become clear, and knowledge of these things was important in what I did at that stage. To show that you had to get singularities under extremely general circumstances. No symmetry assumed, no particular equations of state. You didn't have to assume the dust that Oppenheimer and Snyder had. You could have quite general material as long as you didn't violate energy positivity.
So the obvious thing in the late 60s was to go completely into the new realm of general relativity that's opened up by modern astronomy and cosmology. And what did you do? You started thinking about elementary particle physics.
Well, twistor theory. But it was going along at the same time, yes. Yes, it was. Well, yeah, they were definitely at the same time. But you see, these were things that were nagging at me for a long time. I just couldn't. I have to give Engelbert Schucking a lot of credit here, because on my earlier trip this is the first trip to the States, where I went first to work with John Wheeler in Princeton, and then I went to Syracuse, and I shared an office with Engelbert Schucking. And he kept on talking about conformal maps and the importance of conformal transformations and how Maxwell's equations were invariant. And for what reason, I wasn't sure at that time. But another thing he stressed was the importance in quantum field theory of the notion of positive frequency. And these things stuck with me. And they were very important in the development of twistor theory. Partly the conformal stuff to represent radiation by squashing infinity down, making a conformal boundary to space-time. That was one of the ideas. But the idea of the positive frequency was very crucial to twistor theory. I remember I knew I wanted some kind of geometry which was complex in some fundamental way, but was really trying to describe the world as we know it as well, and had to try and bring quantum theory in. And I made a huge table with all sorts of topics and arrows going between them and things like this. But the Engelbert thing about the positive frequency, which nobody in quantum field theory tended to stress that at that time. It was not.
I think they think of it like physicists generally do in terms of Fourier analysis.
Yes.
So then it's sort of trivial, it's just plus and minus.
I think it was the combination, yes, of the Fourier analysis and the fact that if conformal things were important, Fourier analysis is not appropriate because it's not conformally invariant. Nevertheless, the fact that you're choosing positive frequency as opposed to negative is conformally invariant. And this idea of extending, so you have your Riemann sphere again, you've got your function on the equator, a real valued function, that's the real numbers on the equator. And then if you can extend your function into the holomorphically into the north or the south, this gives you positive and negative frequency. And I thought that's such a beautiful idea. Can that be extended in some global way to the whole of space-time? And this was nagging me, you see. And I wanted something where, you see, if you complexify, you don't have splitting into two halves. You see, this Riemann sphere, you complexify that circle, you've got the Riemann sphere. That's the real part splits it into two halves, and so you get the positive and the negative frequencies. Or maybe I think it's negative and positive, but never mind. And so I kept thinking, well, what about Minkowski space? Well, if you complexify, it doesn't split anything into two halves, you see. But then I remember being driven, I think it was shortly after the Kennedy assassination. I was in America, you see, in Austin, Texas. And the families, respective families, this was the Rindlers and Oshvarts, had gone down to San Antonio. I can't remember where it was exactly. And in the car back, Pish Oshvart was driving me. And he's not very talkative, so there's a lot of silence, you see. And I began thinking about this thing that Ivor Robinson had about how you can take a light ray and somehow push it into the complex. And then you get these funny solutions of the Maxwell equations, which are non-singular and twisting. And so I tried to understand what was going on. And then I realized that these things about the Clifford parallels, I can't quite remember I realized that these solutions of the Maxwell equations must have their null directions along these Clifford parallels. So I knew about the Clifford parallels already, but the fact that this is what you got, I realized this must be what you got, this configuration. So the twisting of the lines around these nested tori, that configuration, which I'd sort of known about from the Clifford parallels. But when I got home, I just translated it all into two-component spinners, and it kind of dropped out, and that was twistor theory. And then you see, you had the thing was split into two halves automatically. You had the space of the light rays, and then it's a sort of mild complexification into these two halves, the right-handed ones and the left-handed ones. And that this was the analog of the splitting of the Riemann sphere into two halves. It took a long time before realizing how it really was that. So it was because it needed the cohomology.
But it's so striking. I mean, now these twistor variables are used by physicists, but they tend to call it a half Fourier transform and think of it in a completely linear way, really. Nothing like this geometric characterization. And yet, if we're going to get away from doing everything in Minkowski space, we really need to have some picture of what a particle is, an antiparticle is, and so on, which doesn't depend on. I mean, I don't know if we may be coming on to this, really. There are things of that period which you worried about, which I think are still very open
well,
now.
It's very interesting. I mean, and as you know, we had this group for developing ideas of twistor theory, and these meetings every Friday pretty well, and discussions, fairly broad-ranging discussions on various topics. And then you, almost single-handedly, developed these ideas of twistor diagrams, and I always admired you how much you felt this was a thing to do, and you stuck with it.
Well, they were your diagrams, but I kept them alive until it could combine with other people's
you developed them in ways
in
which I hadn't conceived of at all.
I'm just thinking I suppose I'm thinking this, you've always worried about what a wave function really is.
Yes.
And a lot of people don't worry about this. They just write down the formalism of quantum mechanics and it's linear and so forth. But you like things that we can see, in a sense. I mean, I think seeing is very important to all you do, whether it's the notation or just the business of light or the action of consciousness and seeing the truth of a Gödel statement. I mean, this is something that's very important. And I feel you don't think we we can see what a wave function is. Would that be a characterization?
Well, I always worried about people saying, "Oh, well, quantum mechanics just tells us pictures are no use anymore," sort of thing.
Yes.
You see, just calculate, forget about the pictures. But I never was happy with that. I always wanted to try and picture anything I could. Certainly with spin, ideas with spin and so on, which seemed to be very important to develop the geometrical ideas as far as one could. But there are certain very odd things about quantum mechanics. Well, I think, as I wrote in one of my books, that Shadows of the Mind, quantum mechanics has two kinds of mystery. I think people tend to confuse them. So the ones I call the Z mysteries, which are the puzzle mysteries, which are things which are true of the world and baffling, but you can understand them. I mean, it's not quite the way we used to think the world was like. Spin doesn't behave like a little cricket ball or something spinning around a well-defined axis. There's something much more subtle going on. But it can be understood, and it's consistent, and it makes sense. And it makes beautiful sense often. And there are the X mysteries. X ones were the ones which were paradoxes, and the Schrödinger's cat. So you have quantum mechanics tells you, without a very difficult experiment, although not so nice on the cat, you can put it into a superposition of being dead and alive. And so Schrödinger was basically showing, well, look, this is what my Schrödinger's equation is telling you you could have. There's a cat which is dead and alive at the same time. That's nonsense. You don't see cats like that. So although he never quite put it like that, it seemed to me he was saying, look, there's something missing. There's something in the theory which is not adequate. And Einstein felt the same way. And Dirac, surprisingly.
Oh, yes, that's Dirac in that, because that's one reason I was interested to hear about.
He was very quiet about it.
Yeah.
He got more. You could see on the web there are some lectures Dirac where he explicitly says this, and I have trouble finding the original quotes because I know there are some quotes where he quite clearly says that the theory is not. Well, he also says in the Bohr-Einstein debates, he says, well, you know, Bohr is normally thought of to have won these, but I think maybe time will tell that Einstein perhaps had more of the right idea.
Did you get that skepticism from him?
No.
In a way? No, that wasn't a feature of what he was
He was
talking
very
about.
reluctant, I think, to express his inner opinions. Very hard. I had a curious experience once. I was asked by the philosophy department at Boston University. You see, the philosophers like to have, a talk given by somebody, and then there will be somebody to contradict him or something, you see. So they asked me if I'd do this, you see. Who was I supposed to contradict? Well, they'd heard about Dirac and commented about how projective geometry had been useful in his thinking, you see. So they had him, and rashly I said, oh, well, okay, I'll make some comments.
But you can't refute that, because that's a marvellous idea.
I couldn't, yes, that's absolutely, yes. So he gave this talk. See, Dirac gave this talk. And it was a very elegantly put Diracian talk on projective geometry. Just on projective geometry. No physics, no influence on his own thinking or anything. It was just a talk on projective geometry. So I'm afraid I slightly made, well, I think some of the audience were hoping you might reveal some of your inner thinking. And then I gave a little talk, since I took a leaf out of his book and gave a little talk on twistor theory, which is now my version of projective geometry in physics. But that was slightly curious. But projective geometry had a big influence on me, of course.
Oh, actually, that's backtracking a bit, but that really would have seemed an old-fashioned subject in your time. It's something that Victorian, I mean, that people just dropped out of the syllabus by that time, I think. Just a little unit here and there.
I just caught it. You see, I went to, when I was at University College London, that's where I did my undergraduate work, there was, in fact, geometry was quite a big part of the syllabus. You had applied mathematics, you had sort of you had applied mathematics, analysis, and then algebra and geometry. I think it was like that. But the geometry was a significant part of that. And there was an old guy called Wren, T.L. Wren, who was a very great purist. He started off, there were just two axioms, there's a line through any 2 points, and if there's a line through these 2 points and through these and it meets there, then these two meet here. How much could you prove from that, you see? Occasionally you needed another axiom a bit later on, but I kind of everybody else hated it, but I rather liked the course, you see. I thought it was very nice to see these kind of very primitive ideas developing into geometry. So there was some projective geometry which I learnt there, which was quite important in my own understandings. Now what was I going to say here?
Well, you brought it back in Dirac's context.
Yes.
And I was just thinking that it did come from your earlier experience. In a way, it was quite unusual.
Yes.
I think.
So it was just, I caught the tail end of it. Well, I think there was there was another geometer who came in after, but then it kind of faded away and got almost removed from the syllabus completely. And then it swung back a bit. Yeah. But it was considered to be unfashionable, and even when you did what was called algebraic geometry, there was very little geometry in the sense of what you could actually see in it. So I didn't take to that too well, although I tried to put as much in as I could. But a lot of it was translated out when I translated my diagrams into some incomprehensible notation, which is, I'm afraid, what my thesis ended up as. But the geometry was always important to me, but it sort of went more into the physics, like geometry of quantum mechanics and relativity, general relativity, that sort of thing.